And there's different kind of ways you can represent this, but here's, in this one they did like a vertical graph. It should be okay.
Yep, I saw it.
So here's your energy, and here's your reactants, and here's your products, okay? And they just got this arrow pointing upwards. So what you guys are used to seeing on the ones we've done, you're saying, oh, here's the energy, here's your progress, and you're going to start with some amount of energy as your reactants. And so what we've done is we've said, oh, okay, well, here's your activation energy, here's your E sub A, and so you can either have a positive delta E, or you can have a negative delta E, okay, based upon relative amounts of energy. So I had like 5 masks.
There's one.
There's one. Nothing up the sleeve, presto. Okay.
No, it was just pop.
All right. So here's the deal. So it's the same type of thing. They just didn't throw in the activation energy part of it. Okay? So your reactants start here, your products end up with more energy. Now, here's what's important. This is for the system. Okay? So it's just like, you know, I'm talking with Isaiah and I said, Isaiah, how'd your weekend go? He goes, man, that's great. You know, I found a $100 bill out in the parking lot. It's like, cool, man. Well, that's a good day. So his bank account went up by $100. So if he's the system, he's had a good day, right? But for him to gain that $100, what had to happen?
Somebody had to lose it.
Somebody had to lose that $100. Okay? So the surroundings is going to see a decrease in that. So we can't measure what is directly happening with the system. We look at what's happening with the surroundings, okay? So it would be like, I couldn't actually see what's happening with Isaiah, but I could see that he's at a higher energy state. I'm going, I don't know exactly what happened, but Isaiah's having a good day, right? So what I would observe is that somebody, then the surroundings is walking around going, man, I have lost a $100 bill somewhere. Oh, okay? So that's the difference between the system and the surroundings. So what you're being told here is that this system is gaining energy. Those products end up with more energy. So energy has to be conserved. So that energy had to come from the surroundings. So if you get an increase in energy of the system, you have to have a corresponding decrease in the surroundings, and that's what we measure, okay? So just keep that in mind. So let me give you some hints. Like on your answer to 55 should be, and you have to be careful on 55 in terms of the sign, because if you look at what's happening on 55, sodium hydroxide dissolved in 100 grams of water, got it out, calculate the quantity of heat in kilojoules, and then you're going to calculate delta H. So here's the deal in terms of sign. So on 55, did the temperature go up or did the temperature go down?
Up.
Temperature went up, right? So is that an endothermic or exothermic reaction? So what does your sign of your delta H have to be? Negative. So this is a situation on 55. You calculate your energy, which is going to be a positive value, but then you switch the sign and you make that delta H a negative value. So in kilojoules per mole, that answer to 55 should be in like in the mid-40s.
So on 55A, does it matter what sign we use?
No, that's going to be, no,
Okay.
but since it technically just asked for the heat, are you my video people?
Yeah.
Oh, thank God. Okay, reach back and stop that camera for a second. Okay.
Feel.
Yeah.
Okay. Ryan, is that red light flashing on the side?
Yeah.
It is? Okay. All right. Okay. On 63, 64, 65, and 66, That is a process, okay? I want to see what you canceled out, what you flipped, did you multiply by 2, by a half, whatever. So your answer to 64 should be around negative 90. And your answer to 66 should be around 150. Okay? Something like that. All right. Any questions on the assignment? Going once? Twice? Sold. So get that handed in. It ain't easy trying to save the plan.
It's not easy. Well, you're only one man trying to save the plan. Your version?
No, I got some help.
You got Rusty at Ford's help.
I did. Yeah, so don't forget, Saturday, if you are 18 or bring the parental units or anyone that's over 18, come up to the school 11 to 4, test drive the Mustang.
Wait, anybody could do it?
Okay.
Anybody that's over 18.
Anyways, over, you have to have 18 and valid driver's license.
What if I were to steal some?
We taking notes
What if you
today?
was to fudge
If I were
the
to steal somebody's driver's license? Mine's Ford.
You know, that's between you and the person whose driver's license you steal.
Okay,
So,
Aiden,
I think we could pull it off. They won't look that close.
Aiden, I may accidentally drop my driver's license on the ground and walking out of the
Aiden, did you get a haircut?
I did.
You shouldn't have cut
They
your
took
hair.
up a little more.
And you should have gotten a left.
You don't like it?
I wanted it a little longer, but
You shouldn't have cut your hair, and then you should get really tan.
Maybe we're still right.
this could
Should I
work.
write this down?
It's not even with the mask on.
Because it's about mold.
Yeah.
I mean, it's.
We got the hair color.
It's pretty close.
Oh
my god.
I weigh 200 now.
Well, the other one.
You just said you're wrong.
Flex it then with your hair.
No, I'm
I
grown.
think we should get a class
Like
pet,
even me,
like a
I'm
class
6 foot.
puppy.
Yeah,
What do you
but-
think?
But
And
six-
you
you're
can
gonna
also-
we're also all-
Einstein the dog.
Yeah, where would that was like you're 6 inches and.
But that's in
Have
they
four
do have the
years.
blue
That's
eyes
4
that
years.
you belong in 2017.
One mole of each.
Yeah, that's plenty of time.
But
That's
you're
prime
6
growing
years.
time.
So what are you having them do out there, Bert?
well, I'm going to make this promotional video
Okay.
that talks about all the different companies that are part of it.
Okay.
And there, so I've got it all filmed and I haven't then just splice it all together.
Oh, okay.
Okay,
If you just.
so this assignment and a bunch of assignments going forward is going to be based upon this data table on page 1088. Okay? So, first off, let me kind of point out some things. So your first column, and this is what we're talking about today, is delta H, and this is what this is going to talk about today. This is what's called your standard enthalpy of formation. So what this column tells you is how much energy is either released or consumed in the production of a compound, and here's the most important part, from its elemental substances, okay? So like for example, there is a whole bunch of different ways you can make water. Combustion reactions of hydrocarbons, decomposition of hydrogen peroxide, the combination of hydrogen and oxygen. There are 1,000 different ways you can get water as a product. But if you're talking about the standard enthalpy of formation, it is how much energy is released or input in the formation of a compound, here's the most important part, from its elemental substances. Okay? That's it. It's the only option. Now, if you notice on this chart, if you go down here, first off, this is in kilojoules per mole. Okay? Your Gibbs free energy table, which we'll get into next, that's also in kilojoules per mole. But this third column that has S at the top, which is your change in entropy, which is a measure of the disorder, that's the only one that's measured in joules per mole Kelvin. So it's not going to be relevant to this assignment, but eventually it will be. So you have your first two columns are in kilojoules per mole. The third column of entropy is in joules per mole Kelvin. Okay, so Entropy is the only one that is in joules. It's also the only one that involves temperature. Okay? So that third column is what makes that unique. Now, so if you look at this chart, like let's say for example you have aluminum. Okay? So if you look at aluminum, its delta H is 0. So all your elemental substances are 0 because there's nothing to produce. Okay, we're not going to combine something to make aluminum. Okay, so anything that's in its elemental form with this delta H is going to be 0. So if you look at like calcium, oxygen, iron, any elemental form, delta H is going to be 0. Okay, so that's the first thing. So this is how it's written. So let's say that you want to make aluminum chloride. Okay? So in a Chem 1 version of this story, you would go, oh, okay, I'm going to take aluminum, and I want to make take chlorine gas, and I want to get AlCl3. Okay? All right? What you got? Now, if you're in a Chem 1, because you all know how to balance equations, so what would that balanced equation look like? Words? Huh?
Hold on,
Okay.
hold on. Just give me a second here. Sorry.
Okay. I might fall asleep.
Berg, it's.
I know.
Let me do this real quick.
Okay.
Keep it up.
Sorry.
You're good.
You go, Riley.
Thanks, guys. Really appreciate it. Shut up. 232.
232.
I knew that.
Okay?
Thanks, guys. Thank you.
Bravo.
I think I need to go back to Chem 1.
Now, and you all would be happy, okay? That's the Chem 1 version of this thing. Okay, it's like, oh, you did chemistry. Yes. Okay.
We just did chemistry. That's
Yes.
PCR.
Go, crew! Yes. Gotta get my Mrs. Short's mood.
You didn't know?
Okay. Now, so here's the deal. So how this would physically play out, you would have a chunk of aluminum, you would have injected in the same container with some chlorine gas, and out of that you would begin to form aluminum chloride, right? So the concentration of your chlorine gas would decrease in the reactant vessel because you're consuming chlorine gas. And aluminum chloride is kind of this white powder, okay? So you can take a poisonous green gas, react it with a silvery metal, and the two of them are going to combine to produce a white powder of aluminum chloride, okay? Yes. Now, but in terms of enthalpy of formation, what you want, this is where you get into fractions. You want the fraction in front of your product to be 1, okay? So we're going to divide all of these by 2. So if you were to write the chemical reaction for the standard enthalpy of formation of aluminum chloride, you would write as Al plus 3 halves Cl2 yielding AlCl3, okay? Now, if you were to actually, then if you wanted to find out what happens in this process, come over here, okay, and you can find aluminum chloride, okay? When you find aluminum chloride, that's negative 705.6. So your delta H of formation is negative 75.6 kilojoules per mole. So if you were to take aluminum and react it in the vessel with poisonous chlorine gas and form aluminum chloride, is that an endothermic or exothermic reaction?
Excellent.
It's exothermic because you have a negative delta H, right? So it does involve breaking some bonds because we'd have to break the bonds that hold the chlorine together. But we're also forming a whole bunch of bonds. So what this tells me is that I've got this big negative delta H. So what that tells me is that the energy that's released in the formation of the bonds that make up aluminum chloride is more than the energy that it takes to break the chlorine apart. Okay? So this would tell me, oh, that's a small amount of energy, but I'm going to get a lot of energy out of it. So if you look at, on a general trend, okay, when you look at these delta H values, if you look down that column, you'll notice that almost, not all of them, but most of them are negative values, but not all of them, okay, but a lot of them are negative values. So what that means is that generally, when you form a compound from its elemental constituents, generally it's going to be an exothermic reaction, but not always. So if you look at, I don't know, iron gas, okay, so if you wanted to make like iron gas, which would be tough to do, right? That's a positive 415.5, because if you think about it, if you want to take iron and turn it into a gas, you'd have to like boil it, which would take a huge input of energy, okay? But when you look down that column, generally speaking, they're almost all negative values. So just keep that in mind. Now, what I'm going to show you is the long way of doing this one. And I'm never going to expect you to do the long way, okay? So don't even write this down unless you want to. I'm not going to do this like calculus where I show you the long way and then 2 days later I show you the shortcut, okay? I'm going to show you the long way because it's important that you understand the conceptual part of the long way. But I'm never going to make you do the long way, okay? If that makes sense. All right, so but it's important that you understand the concept. So here's the reaction that we're going to look at. So 4NH3 as a gas plus 7 oxygen molecules is going to yield 4NO2 plus 6H2O as a liquid. Okay? So visualize this. Here's what's going to happen. So I've got ammonia, okay? Nitrogen surrounded by 3 hydrogens. Now we'll spend a lot of time talking about the cool properties of ammonia. We actually talked about ammonia when we were doing like weak bases, and we put ammonia in water, and it took a hydronium ion from the water and it produced a base, okay? So ammonia can act as a base, okay? So, because what happens with ammonia, and like I said, here's the very condensed version of a much longer speech. So if you look at nitrogen, the hydrogen and the hydrogen. Nitrogen has 5 valence electrons. 3 of them are used up forming bonds with the hydrogen. So it has an unbound pair of electrons at the top that creates this dome of negativity. Okay? We'll spend a lot of time talking about this. That's just kind of the short version. So imagine I've got a bunch of ammonia like this. Okay? And I've got a bunch of oxygen molecules. Right? So I'm going to combine these things in a reaction. And out of that, we're going to break a bunch of bonds that hold this together. Okay? So now, when I break those bonds, is that an input of energy or a release of energy? I got to put energy into this thing, right? So I've taken this stuff, right? Now, out of that, then I'm going to begin to form NO2, okay, like so. So I got some NO2 being formed, okay, nitrogen dioxide, and then I'm also going to get out of that some water, okay. So I'm going to get some water molecules, right? And water also has this dome of negativity. Because it actually has 2 pairs of unbound electrons that are floating up here. So I took ammonia and oxygen, and I'm going to produce nitrogen dioxide and water out of it. Okay? So I broke some bonds, but then I formed a bunch of bonds too. Okay? And like I said, this is the long process. Okay? Don't flip out and go, God, do we have to do this every time? No. But it's important that you understand the concept of it. All right, so here's what happened conceptually. Okay? So we've got your NH3, right? So we had to break the bonds. So on the reactant side, after you break the bonds, okay? So if you were to look at this in terms of how you're going to make the stuff, if you were to look at just making that NH3, right? You would have 2 nitrogen molecules, and you would have a total of 6 hydrogens, okay? So this is how I got that 12. So if you were just to build these, okay, if you were to build these out of their elemental particles. So there's 4 nitrogens, so this is why I have 2 N2s. And then I've got the 4 NH3, a total of 12 hydrogens, so that's why I've got this. So what would happen is that imagine that after we begin to separate this, temporarily they're in this transition state where they're existing as nitrogen and hydrogen. Now, there's nothing to do with the oxygens, okay, because they're already in that elemental form. So those are just going to be 7 oxygens. So those 4 NH3 molecules have the capacity to transform into 2 nitrogen molecules and 6 hydrogen molecules, okay? So imagine that they're separated out and they're going to exist like this very temporarily, okay? They're not going to exist like this very long because they're not stable. Now, out of that, then we're going to form, out of the nitrogen and the oxygen, we'll get the 4 NO2s, okay? So that's going to consume all of the nitrogens. So all the nitrogens are going to get used up in making the NO2s. I'm going to use part of the oxygens here, so I'm going to use 8 of those oxygens here in making the NO2s. The rest of them are going to be used to make water. So then I'm going to take some hydrogen and oxygen, I'm going to combine that and get these 2 O liquids. Now, here's the vital part of the water. If you look on this chart, we talked about this on Friday. So one of the things that you have to pay vital attention to is that when you get to the oxygen section, and that's where water is, okay? Water is with the oxygen section. You have water as a gas, and you have water as a liquid, okay? They are completely different thermodynamic data. So when you look at an equation, you have to pay attention. Is this gaseous liquid water, or is this liquid water? Because the thermodynamic data is different. Now, the other thing that you'll tend to do in a rush is that you'll tend to look at the hydrogen peroxide, which is just below that, okay? So pay attention to the water, pay attention, is this liquid or is this gas? And so that's the important part of this, is that it's a liquid water. Okay, now, so here's what we're going to do. And like I said, don't flip out and go, God, do we have to do this? No, you don't. So here's what happened. The NH3 is going to decompose into N2 plus, okay? So, but that's going to happen 4 times, okay? So what would happen if you do like the reverse of the enthalpy of formation? We would take the NH3 and break it up into its elemental forms, okay? This is just the reverse if I said, hey, party girl, write the equation for the enthalpy of formation of ammonia. So she would write it as 3/2 H2 plus 1/2 N2 making NH3. So if she was making it, she would reverse this. But we're decomposing it, so we're going to write it in this direction. And that's going to happen 4 times because there's 4 moles of this thing. Now, if you look at what's going to happen, so if you look on your chart, so if you come in here and you find nitrogen, okay? So underneath nitrogen, you have ammonia gas, which is what this is, okay? This isn't ammonia dissolved in water. This is ammonia as a gas. So notice that's negative 46.19. Now, so this is what you want to think through. That's negative 46.19 as the enthalpy of formation. Okay? So it's negative 46.19 as the enthalpy of formation. What's it going to be as the decomposition of ammonia? Positive, because we're going to reverse this thing. So if I make ammonia from nitrogen and hydrogen, it's an exothermic reaction. But if I take ammonia and I decompose it into nitrogen and hydrogen, then it becomes an endothermic reaction. Okay? So let's do us a favor. We're going to make that positive 46.19.
What is it?
46.19, but that's going to happen 4 times. So multiply that by 4, and what do you get?
184.76.
184.76. So notice that that's a positive value. So that's how much energy is input to break up the ammonia. Okay? All right. Now, we don't have to worry about the oxygen because that's already in its elemental form. Okay? So there is no value for the standard enthalpy of formation of oxygen because it's just a number. That's all it is. Okay? Nothing there. 0. Now, we need to make NO2. So we're going to write this as 1/2 N2 plus O2 yielding NO2. Now, if you find that value, okay, so you go to your nitrogen and you find NO2, that is 33.84. Okay? Now, that's a positive value as it is written. So what this means is if you take nitrogen and oxygen and try and make NO2 out of it, that's a positive value, right? It's an endothermic reaction. So remember, and we'll talk more about this, Mother Nature doesn't like endothermic reactions because she doesn't like giving up energy, okay? Now, do you think, and we talked about this before, do you think this reaction between nitrogen and oxygen to form NO2, do you think that's a spontaneous reaction? No. No. What's our atmosphere made of? Nitrogen and oxygen. If this was a spontaneous reaction, guess what? Our atmosphere would be made of
Air molecules.
or nitrogen dioxide. Okay? And then we wouldn't have free oxygen available to use in redox reactions. So we'd never, well, we just never.
And we'd never do redox reactions, and the world would be good.
And we just wouldn't be here to have it. The world could be here, we just wouldn't be a part of
We'd
it.
have nitrogen dioxide gills.
Yeah. Okay.
Excuse me?
Now, so here's the story. That's going to happen 4 times.
Yeah.
So take 33.84 times 4.
That's gonna happen 4 times?
Yep.
Oh.
Because I want to make 4 NO2s.
Oh, I thought it was only 2. 135.36.
135.36. Okay? Now, here's the last one. We need to make liquid water. H2 plus 1/2 O2 yields H2O as a liquid. And that's going to happen 6 times. And for water, what's water? Negative 285.83.
Negative 1,714.
What'd you get? Negative what?
1,714.
Oh, hold on. Negative what? 1,000?
714.98.
kilojoules.
Sure.
Okay. So, here's what we're going to do. So, we've got 2 endothermic reactions, one at 184.76, another one at 135.36, and then we have a very exothermic reaction from the formation of hydrogen and oxygen to produce water. And Tate can attest that hydrogen plus oxygen is an exothermic reaction. Okay? Tate is living proof of that. You can go, oh yeah, trust me, that's exothermic, right? You felt that energy being given off. So, now, words, add all these together.
Okay, so.
Take negative 1714.98 plus 135.36 plus 184.76.
Plus 184.76 plus what?
135.36 plus negative 1714.98. Basically add the three values that you already found.
Negative 1394.86.
Negative 1394.
0.86.
Okay. So is this overall reaction endothermic or exothermic? It's very exothermic, right? We're going to get a lot of energy released from this process. So what this means is if you take ammonia gas and react it in a pure oxygen environment, you're going to produce NO2 and liquid water. Okay? So you're going to get a lot of energy that's being released. Okay? So this would be very exothermic. So this reaction vessel would heat up. Okay? Right? It would very much heat up. So this is the long way of doing this, where you break it into, but it's the long way, but here's what I want you to understand, is that when you're looking at these values, this is fundamentally what happens. Is that, okay, how much energy is involved in the formation or breakdown of these compounds from their elemental substances? It's important that you understand the process, but we're not going to do the process, okay? So here's the short version, okay? Now, this is what's on your equation sheet, okay? So let me see somebody's equation sheet. So what you have back here on this sheet, third equation down, is this. So you have delta H is going to equal the sum of your delta H of your products minus the sum of your delta H of your reactants. Now, you notice that there's three different versions of this, okay? There's your delta S, which is your entropy, delta H, which is your change in enthalpy of formation, and then you have delta G, which is your Gibbs free energy. Notice that all of them have the exact same format, okay? It's always products minus reactants, okay? That's it. It's the exact same format in all of them, okay? There's no variation on the theme. It's always products minus reactants. So just like when you're calculating Q, and that was always products over reactants, this is always products minus reactants. You don't have to think. It's like, is this reactants minus product or products minus, I don't remember, okay? You don't have to think that. It's always products minus reactants. Okay, there you go.
Oh, thank you.
So here's how you're actually going to do this, okay? So let me rewrite the equation. So you got 4NH3 okay? So here's all you got to do. So instead of writing them down, writing out the equations and all of this good stuff, here's all you got to do. So you can take your products, the sum. So you have 4 NO2s plus 6 H2O waters as a liquid minus your 4 NH3s plus your 7 oxygens. Now, because you're talking about delta H of formation, do you have to worry about the oxygens?
No.
No, it's an elemental form, right? So if you try and find the heat of formation of oxygen, guess what? It's not there. It's a 0. Okay, don't worry about it. Okay, it's not. You don't have to worry about it. So you got that one. So now the beauty of this process, this is why it works. You don't have to flip the signs. Okay. You don't have to do anything. All you have to do is look up the thermodynamic data. That's it. Now, what some people like to do, they'll take like a sheet of paper and they'll slide that on this page, so that way it's easier to like keep track as you go across visually, okay? So some people might, though, use like an index card, they don't even have to have a full sheet of paper. But so, because you're gonna spend a lot of time staring at all this data, and your eyes tend to get a little bit blurry after a while. So generally, here's what I found. So kids generally don't struggle with the process. If they make mistakes, it's because they wrote down the wrong numbers out of the page, okay? That's the most common mistake that is made. Trust me, been there, seen it. That's what happens. All right, so here's what you're gonna do. So you got your 4 NO2s, so that's gonna be 4 times, and again, I'm gonna write out the long process. 4 times your NO2s, plus 6 times your waters, minus 4 times your NH3s. Okay? Is going to equal the sum. Now, later on you'll see how we actually got these values. And the reason that you want to be able to think through it this way is that sometimes what you'll do is that you'll know like the overall enthalpy of reaction. Okay? You'll know what you run the reaction, you know what this is. So what can happen is that, okay, hey, you might know what the values are for NO2 and H2O. Okay, you look at the back of the book, you've got those values. And you actually run the reaction, and so you know your overall delta H. But if this is your unknown, then if you know your overall reaction, you can solve for this as a variable just like you would anything else. So that's actually how we generated these values, is that it was like a puzzle. And we put together the beginnings of the reaction. Oh, hydrogen and oxygen. Okay, let's get some data for that. Okay, once we got water, then we could expand that. Okay, what does water react with? Okay, maybe water reacts with calcium and to produce calcium hydroxide. Okay, that's a very exothermic reaction. So then we can figure out, oh, okay, just what's involved in the calcium hydroxide production. So if you have water and we know the overall reaction, then we can figure out, oh, what happened with that formation of calcium hydroxide, okay? So a lot of times what you do is you'll measure physically in the lab, you'll measure the overall reaction, and then you'll know 2 or some of them, and then you solve for an unknown value, and that's how you fill in the gaps in the chart, okay? So you're going to take 4 times the NO2, which was what?
33.84.
Yeah, 33.84. Plus 6 times your water, which is negative 285.83.
It's plus the 6.
Yeah. But it's going to be 4 times 33.84 plus 6 times
I
a
know.
negative.
Yeah, I knew that.
Yeah.
It was just-
And then minus 4 times 46.19. Okay? Now, here, but you have to watch the signs, okay? When you punch this into your calculator, you have to watch the sign. So you've got this plus this, so here's the sum of your products, and then your reactant is only the 46.19 times 4, because you don't have to worry about the oxygen, okay? So, what'd you get?
I'm doing it right now.
Hopefully, you get this.
It's not 6.
Should be,
4 times 33.84, right?
yeah.
Okay. 6 times negative 285.83.
Yeah, and then get the sum of that.
Add that together, right?
Yeah, and
Okay,
then
got that.
minus.
And then 4 times 46.19 minus this.
No, that 46.19 is a negative value.
Okay, that's why it was wrong. Thank you. Yeah, then I got that. That 46.19 is a negative value?
Hold on. Yeah, your NH3 is, yeah.
Yeah.
Yeah, that's a negative 46.19.
Then
And then you-
negative 1394.6. We're good.
Okay, got it? Good? Okay,
Are we done?
we're done. We are done.
Do you have any sign up for us?
What do you think? Works?
Nope, never.
Yep.
I wish. I know I did the survey. Can you imagine?
No.
They were on this one. That would just be, you'd just be too nice. Because I have two minutes. Ryan, how was the lecture? Bless you. I don't know the difference.
I was gonna ask.
Dude, is Kelsey dead?
On like the right side,
No.
she's getting it as negative. I don't know.
Kelsey, you look dead.
No,
So is Tate.
where?
I don't think you
Hi, Tate.
Tate, are you okay?
Add it, and that's.
Tate wants to sleep. Sleepy Tate.
Probably because I got 5 hours of sleep last night and.
Really
Why is
gonna.
that? I don't know how to
You
go.
didn't call it,
Like,
wait, yeah,
like,
wait, what is that?
5 hours.
Yeah, what
I
is
don't remember
that?
ever
On Sundays to go fly an airplane.
How was that?
That's
Yeah.
fun.
Does that say 73?
Tate,
I don't, when did we?
was that the RV-12? I was supposed to get to fly that one, but
So yeah, what's the?
they canceled the day they scheduled me to fly because of bad weather, and then they just never called me back to schedule.
No, that's high
The direct.
75, 71.
It's okay, because around the same time I flew, one of my family friends is a Piper Cherokee.
And then 81. But is that?
I'd rather fly the Piper than that RV-12.
Dope. Thanks, Bert. Let's do it. Do you want me to turn this off?
Let's steal.
All right.